class. Today we're going to finish up our matter unit and then start heading into energy. So there was a few more things that I wanted to cover before we move forward with our energy unit, which we will be starting midweek. So just looking over this information, I just wanted to bring up a few other things under the heterogeneous and homogeneous mixtures discussion that we had earlier. So getting underneath of our suspension. Suspensions is considered a heterogeneous mixture, and generally the particles that are suspended inside of this mixture are greater than 500 nanometers in size. So because of this, they're a little more on the dense side, and as a result they will generally settle to the bottom and sometimes even to the top. It just depends. But the main idea here is that it will actually suspend out and go somewhere. So an example of this would be, here we have some water, and then we just put in a few like sand particles. So let's get some sand particles in here. Just put some little sand particles. And whenever you are first mixing it up, it may seem like it's a homogeneous mixture, but you will rapidly see within a short amount of time that this will actually settle out to the bottom. Okay, so this is an example of some sand in the water. So another example would be paint. Maybe you have opened up some paint in the past and you have noticed that the colors have separated from the rest of the paint, and you have to mix it up a little bit before you can go ahead and apply it. Another example would be chocolate milk. I'm not sure if you've ever put too much chocolate in your milk, but you stir it up and for a long time it looks nice and homogenized throughout, and it actually looks like it's a homogeneous mixture. But shortly you will see that if you supersaturate your chocolate in your milk, your chocolate will generally fall and settle to the bottom. In that case, it would be considered a suspension. Okay, let's move on to a next thing. Another type of mixture is considered a colloid, and these are generally between 200 to 500 nanometers, or particles that are small enough to stay suspended and hold together. So a few examples of this would be like jello, mayonnaise, milk, ice cream, and even fog. Fog is just more in the category of water droplets that are suspended in the air. So that would be considered like an aerosol type. So to kind of continue this one, if you look, we have something called Brownian motion, which means it's the erratic movement of colloid particles. And how we can determine if we have a colloid or not is by something called the Tyndall effect. With the Tyndall effect, if you took, let's say, some milk, this is all milk, okay, and you try to flash a red light through it, or any light, you'll notice that the light will scatter. It will not just go through. Okay, so it'll kind of scatter this way, this way, this way, this way. It'll stay kind of generalized right in this region. Kind of go up, kind of go down. Now, since red has a shorter wavelength, it'll probably go through a little bit better than, let's say, a blue with a shorter wavelength. The blue would actually disperse in all kinds of crazy directions, but not physically go through. Now, how we can actually apply this into the real world is think of fog whenever you're going out at night. Not sure if you're driving yet or not, but your parents at some point in time have probably had to use some sort of special light to get through the fog. Did they use their high beams? If they did, what happened? So I'd like you to think about this for a little while. We would not use high beams, hopefully, in fog, and I would like you to explain why. And tell me what you or your parents would use instead. Okay, so that's a little bit about a colloid, some examples as we had just mentioned earlier. You think of mayonnaise, particles are small enough to stay suspended. It generally does not start to dissociate into different particles unless, of course, it's been in there for a while. You might see it a little bit runny, but generally speaking, it should stay pretty well held together throughout. milk, once it's been homogenized, whenever you first get milk, of course, if you've ever been to a farm, you'll see some fat up on the top, and then you'll see it'll be like watery towards the bottom. Well, whenever you get homogenized milk, they actually make sure they spin this really well until it looks homogeneous throughout. And that's whenever we get this colloid type of mixture afterwards. Okay, our final type here is called a solution, and these are smaller particles below about 200 nanometers. And an example of this would be salt in water. As you recall, salt is the solute and the water is your solvent. They create what we call an aqueous solution, and this is what we mostly use in chemistry. So if we're moving along and we're using some sort of chemical equation like salt in water, you're going to see maybe this was a solid as a state symbol, this was a liquid, and they form together to make what's called, you'll see this in the future, an AQ, an aqueous solution. Okay, so just this actually won't make an actual chemical equation, so because they don't actually react that way, they stay together. As you recall, this is a physical change, NaCl and water. Nothing's really changing. All you get is some salt water, but what you did create was an aqueous solution. So hopefully this will help your understanding of these special types of mixtures. You will now go ahead and complete your bell work whenever you get into class tomorrow morning. And from there, you'll have a worksheet that will just help to solidify these concepts. And then we will be moving on to our kinetic theory. So you'll be on the lookout for that video to watch, and we will continue with our energy unit following this. Okay, well, have a great week, class.